We're going through a phase change in our energy infrastructure. With batteries, solar, efficiency, and wind, we're heading towards basically electrification of everything. I'm going to talk about one critical part of that, and that's silicon photovoltaics. PV installations grew by 10x in the last 8 years. Here is a better way of looking at same information provided by ITR PV. This is basically the PV analog of ITRS. And this is their most aggressive deployment scenario. The yellow line is the projection. The blue line are actual. 2017 actually saw over 100 gigawatts of solar deployed worldwide. Now, there are two ways this could go. We could stall, which would not be desirable, or we could go even faster. I'd like to point out three things here. The key difference between the red line and the blue line is the rate of deployment, how much solar is deployed per year. Two, the blue line shows the next 10x, going from 100 gigawatt a year deployment to 1,000 gigawatts, a terawatt per year solar deployment. And three, this dashed red line on total deployed projection of solar, that's 18 terawatts. That's primary energy use of humanity. So why can't we deploy silicon PV 10 times faster? It's cheap enough. It's actually very efficient, but not fast enough. There's actually a physics-based reason why that's the case, and it's this. It's the silicon solar cell. This is a high-efficiency silicon PV cell, but it's a crystal. You can't really bend or flex it, so therefore you have to put glass, aluminum, other structures around it, and that's really what limits it in terms of its speed of deployment. What if you can take that same silicon and do this with it? It's still the same single crystal high-efficiency silicon cell, but now you can change how you assemble, ship, deploy, and operate based on this transformation. You can think about polymer-embedded structures, very thin, ultra-strong glass around this, that now allows you to embed this into building materials. Any structure that you deploy can have energy harvesting capability built inside of it, rather than as an afterthought. These are things that you can deploy, recover, and redeploy many, many times over, and it can last decades, 50 years, 70 years, or more in certain cases. So, what if we can deploy silicon PV 10 times faster? Where does that take us? That's where we end up. We will be able to deploy a terawatt of silicon per year and achieve energy access in a scale that we haven't had before. Now, there have been some very strong arguments about 100% renewables. Can we do it? We can't. We can't do it. No, we can. Yes, we can. That's the wrong question. I believe the key question here is, why stop at 100%? This is a recent paper from colleagues at Sandia National Laboratories and two other institutions showing the abundance limit of excess energy generation on the surface of the Earth at about 600 terawatts. That's about 30x our current primary energy use, with only 0.2 degrees C temperature rise, taking into account the albedo effect and all the other consequences of that extra energy consumption. With all that excess energy, we need to do one thing very quickly, and that's this. We need to capture carbon dioxide out of the air to prevent runaway climate change. This is from very recent Shell Sky scenario, again highlighting the accelerating rate of electrification and the fact that we do have to deploy CO2 capture and sequestration. Otherwise, we need to talk. This is a critical thing that we have to do, and we cannot delay. There's really no time left for us to be able to achieve what we need to achieve in the next 50 years to reach the net zero emission conditions. And with that, thank you very much.